So my specialization is in two fields, really the field of ecohydrology, which really grounds in the natural sciences and sort of my background in physical chemistry, and also water footprints, which is a totally different area. And my experience is that some people have heard about what a water footprint is, but don't really know the full story. I've been following the story for almost 10 years, so I've been lucky to see this field sort of evolve and emerge. And I thought it'd be really good to give you a summary of what that story is, and also with a very important point to show these two different aspects of this, what a water footprint is. And that's the title of my presentation, which is freshwater volumes and impact assessment. So I want to zone in to the importance of consumption and production. So from my background in industry, I really like to focus on consumption and production of products and services. And we know that agriculture and industry are, and their production and consumption activities consume large amounts of water. Also, if you think about the life cycle of a product, so by that I mean the entire life of a product from resource extraction all the way to the end of life, and here we have an image of what that looks like for an agricultural product. About 90% of water withdrawals globally basically relate to one or several phases within this life cycle. So that's a very interesting observation. If you actually look into how companies are reporting on their water use, and this is some work from out of the Netherlands, Linman et al., that basically created this scorecard for companies and looked at, basically applied this scorecard to companies listed on the Dutch Stock Exchange. They found that even the best company that reported on their water use only, and this is Heineken, number one on the list here, the company basically only could get about 50% of their mark, mostly because the water use that's being reported by the company relates mostly to their operations and not their supply chain. And that's really the sole sort of the idea behind the water footprint, is to bring to light the full water story in terms of consumption and production. Starting in the early 90s with the idea of virtual or embedded water, perhaps you've heard this term before, that Tony Allen used in the late 1990s, basically to describe international relations, saying that if water-stressed countries could basically reduce conflict, mostly in the Middle East and Africa, which was the interest of Tony Allen's research, and they can reduce that stress by importing water-intensive products. So the idea is that get other more water-abundant regions to make those products and sell them to them so that they can use their water resources for other purposes. So that idea was carried out quantitatively later on. It started qualitatively and then moved into the more mathematical aspect of the water footprint with a publication by Hoekstra and Hung in 2002, defining the water footprint really as a freshwater volume, looking at consumptive use. So we're really looking at the amount of water that's used or evaporated, so either integrated into a product or evaporated off from the watershed. Basically, it's water that doesn't return to the watershed. And there are two components. There's a direct consumption, which is your drinking, your washing, your direct water use, and the indirect consumption, which is the water that you're consuming indirectly through products, services, or your supply chain if you're a business. And then through that calculation, you basically get what people are typically known to be water footprints. For example, that you require 300 liters of water for 1 liter of beer. So typically, people are more familiar with this side of the story, but the story doesn't end there. Very quickly, things started moving in the field of water footprint with the release of what was called the Water Footprint of Nations, the creation of the Water Footprint Network in 2008. That's when I started looking at master's programs and came back to UBC, and the publication in 2011 of a standard by the Water Footprint Network and its partners to basically normalize the methodology. And from that, basically started the two subfields, I would say, one which is called virtual water trade analysis, and then the water footprint sustainability assessment, starting with the virtual water trade analysis, which is one subfield of the water footprint field, if I could call it that, basically quantifying a lot of the things that Tony Allen thought about qualitatively. So calculating actual trades of those water volumes with products, and trying to see if there could be any kinds of savings, global water savings with trades of those products. And then the other subfield is called the water footprint sustainability assessment, which in which you look at the water footprint within a certain boundary, let's say a watershed or a country, and you compare it to a maximum sustainable limit. So that could be true for water if you're looking at the water footprint. It could be true for the carbon footprint as well. And actually, there's some work now trying to integrate a lot of these things together: the ecological footprint, the carbon footprint, and the water footprint. So that's one side of the water footprint coin. The other side is the appropriation of the term by the life cycle assessment community. And life cycle assessment, for those of you that are new to the term, going back to the life cycle of a product, the life cycle assessment community is interested in looking at the entire life cycle of a product again, but then looking at impacts. So those could be economic impacts, social impacts, but in our case, we're interested in environmental impacts. So what you do is that you look at the all of the inputs going through a production system, and then quantifying a lot of the emissions of that production system, running it through a model, and basically figuring out what those environmental impacts would be to typically human health, natural resources, and ecosystem quality. So in 2007, the life cycle assessment community realized that impact assessment, the impact assessment methods at the time did not include water consumption. So that was a very important paper that was published in 2007. From there was created the Water Use and Life Cycle Assessment Working Group, which, while the volumetric water footprint community started thinking about ways to look at water use efficiency and other strategies, the life cycle assessment community started producing or going through several developments of their own, culminating basically into an ISO 14046 standard, which defined the water footprint as a life cycle assessment that is mostly focused on water consumption. So you can see how things get pretty confusing, because you have these two different ways of looking at water consumption for industrial products. Now, just to summarize these two different ways of seeing the water footprint, we have a more volumetric focused water footprint, which is the more traditional way of looking at things. That community is more groups, people that are interested in water resource management, for example. And then we have the impact assessment side, which is the life cycle assessment community, typically more engineers. And this is how they look at water use in industrial products. On the one hand, you have the consideration that water is a global resource, and we must look, therefore, we must look at local consumption efficiencies and gains through trade. That is the objective of those that focus more specifically on volumes. On the other side, the impact-focused or LCA-focused water footprint, for them, the water consumption has an impact on local resources, which should be the focus of product environmental performance. Two different ways of addressing water. first group considers total water consumed and polluted within maximum sustainable boundaries. So really, they're concerned about not exceeding some sort of boundary that needs to be defined. Whereas the LCA community is more concerned about stress-weighed water equivalence, basically saying that 1 liter of water used in a desert or a highly stressed area is not equivalent to 1 liter in a water-abundant region, because the impacts would be different. Soil moisture, so I'm going to be very stock specific here, is an important resource and should be included. So you can think of why that would be important, mostly because of rain-fed agriculture. So that has to be included as well. On the impact side, this soil moisture replenished by precipitation, which is often called green water in the literature, has no impact, so it doesn't really need to be included. And finally, to summarize in one sentence all of the above, on the one hand, sustainability is viewed in absolute terms versus relative terms if you're thinking about life cycle assessment. I'm going to focus now, I'm going to bring ecohydrology back into this and describe how this could be applied in the context of soybean production in Amazonia. So Alicia already gave a brief introduction of the region. I'm going to talk more about water resources. And this is the Amazon basin, about 7 million square kilometers, with the state of Mato Grosso, which Alicia also described. What's interesting about the location of that state, which is about the size of BC, is that it's located upstream of major tributaries of the Amazon. So a lot of the conflicts, the land use conflicts that are occurring in the region can have impacts on water resources. For example, a lot of deforestation in the tropical forest and savanna biomes, so that deforestation happens for cropland expansion or pasture, for soybean, corn, but also cotton, and a lot of beef production. The fastest growing business in the state of Mato Grosso is aquaculture, so land-based aquaculture for fresh fish, using the very crops that are grown in the state to feed the fish. And finally, this area is very far from the coast, so the concern about infrastructure and how to export those products also has some repercussions on water resources, especially if you're thinking about hydroways and development of large navigation hydroways to export the commodities, and how that would conflict with conservation of aquatic ecosystems. So my question mostly in my PhD is can a water footprint approach provide insight into water use in the region, thinking about both the volumetric side and the impact assessment side. And the general steps, which I'm just going to describe briefly here, is to look at all the products that are the agricultural products that are being grown in the region. Soybean, maize, cotton, sugarcane, all of those are rain-fed. So there's basically no, I think it's 99% of it is rain-fed. There's very little irrigation in the region. We take key parameters from the cropland and the pasture to be able to model water use for agriculture, and then we can scale things up to the watershed level ahead of looking at a volumetric-based and the impact-based water footprints. So on the one side, I'm really interested in looking at the water use information and looking at the change in water consumption over time, and then looking at the impact assessment from that consumption and how that might impact ecosystem quality mostly. So we have to do some measurements, which I won't go into this year, perhaps next year, and then we have to think about the impact pathway. So how does a water consumption activity affect impact and the impact to ecosystem services? So just very briefly to give you an idea on one particular impact pathway which is of interest. Any land use change will create some sort of disruption to the hydrological cycle, starting with the natural condition on the left-hand side of the screen. You have a certain amount of discharge, a certain amount of water vapor being returned to the atmosphere through evapotranspiration. So that's the amount of water evaporated or transpired by plants. And that water vapor returns to the landscape as rainfall. Now, if you look at, for example, deforestation of a deeply rooted tropical forest to a short-rooted pasture, you will get some local scale disruption with a decrease in evapotranspiration. So the amount of water vapor is diminished. The amount of water vapor going into the atmosphere is diminished. That results in an increase in runoff and also an increase in discharge. But you also have another regional scale disruption, which is the slowdown of what we call the precipitation recycling. Because if you have less water vapor going into the atmosphere, you also have less precipitation. And if it rains less, then you get a decrease in discharge. And that's really what we're interested in modeling here. And the missing link here is soil moisture. You go from, for example, a forest-dominated landscape where you have a certain amount of evaporation happening and precipitation to a cropland where that recycling is diminished. And if you look at the Amazon as a whole, that ratio is about 30%. Now, the proposed impact pathway is one that would link land use change to an impact to ecosystem services, an impact to terrestrial ecosystem damage, going through what we call a midpoint impact of a reduced precipitation. These are just a few of the models. This is a very new field, so there's basically everything that has to be done. The oldest model here dates back from 2009. So we're thinking about how a land use change activity would affect evapotranspiration, which itself would impact precipitation, and that reduced precipitation would impact ecosystems in a way typically killing off very older trees due to a lack of soil moisture, some recurring droughts, etc. So in the life cycle assessment way of looking at things, we really want to think about a logical cause and effect chain of how we would link land use change to ecosystem damage, starting from the square meters of land transformed, so let's say forest, to a change in ET, or evapotranspiration, from a forest to a soybean field, which itself would impact the amount of precipitation returning to the landscape. And that reduction in precipitation can affect the amount of species that are present in the region. So I'm not going to go through the mathematics of this. If you're interested, we can discuss this offline. But basically, we can model the change in evapotranspiration. We can model as well the atmospheric water balance to figure out how much precipitation is missing. And we can also figure out the impact to species richness from a water energy regime that can help us quantify the damage to ecosystem quality. So very quickly, as my last slide, just some very preliminary results, looking first at some initial crop modeling results, which will have to be confirmed by measurements, that for the region, soybean requires about 1,900 liters per kilogram of water, which at the state level represents 28 cubic kilometers per year. So if we're looking at maximum sustainable limits, which we still have to define, in terms of volume, that represents one Itaipu Dam, which is the biggest reservoir in Brazil. And if we look at the impact assessment from the model, the method which we're proposing, we can see that we can calculate how 1 ton of soybean produced on about 3,000 square meters of land from previously occupied tropical forests can affect precipitation recycling. So we can look at the entire Amazon and then the Xingu basin. So if we look at changes in precipitation, that represents about 700 cubic meters per ton of soybean produced. And then the damages to ecosystems, we're looking at about 200 potentially disappeared fractional species square meter a year. That's a typical unit in life cycle assessment. And we can basically relate land use change to impact damage to ecosystems. And I'd like to thank UBC, the IRES, and CREG as well, with whom we are actually working on this. Okay? Life cycle assessment, yeah. Mm-hmm. It depends because you have to figure out what your product is used for. So life cycle assessment has a few ISO standards which have to be followed. And typically the very first thing is you have to define your scope, your goal and scope, and within that you have to define what the function is of your whatever you're looking at. So typically, one example could be you want to wash your hands, you want to dry your hands 10,000 times. That could be one thing. A pair of shoes, from extraction of the components that go into making a pair of shoe all the way to the day you throw out your shoes. So the impact will always be referencing that function. So you will be figuring out, for example, how much eutrophication is happening per 10,000 times you are drying your hands, for example. In agricultural products, we're really more at the resource extraction phase. So we're typically using kilograms. 1 kilogram, 1 ton is often used, but that changes very quickly once you look at a finished product, a cup of coffee, a can of Coke or something like that. Mm-hmm. Yes. Mm-hmm. All the inputs, anything you can think of. There are databases that are very big with thousands of inputs. It can be anything that goes into making your plastic that's used to make the bottle that's used to put the Coca-Cola inside. Yeah. So to answer the second question first, the goal of the virtual water trade analysis is to identify savings from trade, but savings of water, and to see how globally water resources could be used more efficiently. So a lot of the studies began globally, but now there's a lot more national studies happening. There's one for the U.S., a very detailed one for China, actually. Um, yes, exactly. Or if rainwater is used more efficiently in one area, that reduces the need for irrigation in another area of the world, for example. That's the idea. Now, in terms of the volumetric analysis, let's say, going away, nothing is going away actually, because it's a very young field, I would say. Yeah. Okay. Yeah. Right. Right. Yeah, so in Europe, there's more a push towards environmental labeling. Now, whether they have water or not is, I think it's really dependent on the country. There's definitely some pilot studies I've seen in France, using, for example, on your bill, you have amounts of CO2 equivalents, things like that. I know that if you want an environmental label in the EU, you have to do a life cycle assessment, which doesn't mean you have to compare anything. It just has to be verified independently, and then you can put on an environmental label. And there's about something like over 60,000 products that have the label. Now, that's where things get tricky, because you have to do a life cycle assessment, which means you have to follow one of two possible ways of doing a water footprint. So that also creates some tension within the field of these two ideas sort of saying, well, our way of seeing things is what is more important, and the other side saying, well, that doesn't really help water resources management because A, B, and C. And it's an interesting debate actually happening in the field, I find. So. Yeah. Yeah, so you're deforesting for soybean, and that, yeah. Mm-hmm. Yeah. Yeah. So the piece here is that this can now be included in a life cycle assessment. So if someone wants to do a life cycle assessment, and actually right now, if we did if a consulting firm in Europe did a life cycle assessment about soybean, Brazilian soybean being used in a product, these impacts wouldn't be included at all. Like, there would be basically zero impacts here, because the models don't exist. So there'd be all these other impacts that are pretty well modeled and available, but this part wouldn't exist at all. It basically wouldn't appear. And that's true for water, and that's true for land use change, actually. So these working groups have been put together so there's the water use and life cycle assessment working group, there's a land use change working group, have been put together just to provide recommendations to the life cycle analysts on the best methods and practices to be able to include these impacts, so that companies can look at their supply chain, look at their impacts, and make decisions based on those results. Basically, if there's no way to measure it or to calculate an impact, it shows up as inexistent. And that's true for biodiversity and many other impacts. Yes. Yes. Yeah, exactly. Exactly. Of course, this is only one side. You'd have to include all the fertilizer, you'd have to include all this other stuff, which already exists, so get a more complete picture. Thanks.